for having me here and for coming to this talk. So I'll be talking about this model of random geometry, which is called Liouville quantum gravity. So this is a continuous model of random geometry, and it arises as or it is believed to arise as the scaling limit of certain discrete models of random geometry. So I'll first tell you some stuff about the discrete model, and then I'll just give you an overview of the area, and then we'll talk about the specific question that we are of this talk. This is about representing the boundary length as a variation process of a distance profile. Okay, so let's begin with the discrete. Maybe I'll push this out. Okay. So discrete objects, there are these things called planar maps. So these are very simple objects. So objects are these things called planar maps. So they are just, think of them as you take a sphere and you draw a graph on it, right? So suppose you have so for example, a planar map can be an object like this. So here you should think of this object as being drawn on a sphere. So the stuff outside, the outside thing you should consider as one face of the planar map. So this whole thing wraps around and it's drawn on a sphere, right? So such objects, such planar maps, you can think of them as measure metric spaces. So what do I mean by that? I just mean that you can consider each edge to have length 1 and each vertex to say have mass 1, and then you can endow a measure to this planar maps by to each planar map by I mean, you can just think of the counting measure on the vertices, and the distance on the planar map is simply the graph distance, right? So then once you have planar maps, you might want to ask, how does a uniform planar map look like? So for instance, you might ask, okay, so suppose I sample uniformly from the space of all planar maps which are quadrangulations. So in the sense that each face is can only have parameter 4, so you only have quadrangles glued to each other, and you look at all quadrangulations with, say, perimeter or with total mass n, so n vertices. Sample uniformly from the space of all quadrangulations with total n vertices, and try to ask, what does a typical sample look like? So for instance, what's the perimeter of such a sample, or what's the total diameter of such a sample, right? And these things have been studied. There's a whole community of mathematicians who study uniform planar maps. So the first, maybe I'll show you a simulation. So yeah, so this is a simulation where they take a large quadrangulation, a large uniform quadrangulation with the topology of a sphere, right? And you can, this thing, okay, this is topologically a sphere, though I mean, as you can see, the metric structure is not what you would usually expect from a sphere, right? It looks quite weird. But so yeah, so typical, and you can see that there is, I mean, it looks weird, but it does seem like there's lots of structure. So yeah, this area of uniform planar maps, it's trying to uncover this structure in such objects. Okay, so in the next slide, now I'll tell you about some results. Right, so this area is known as Brownian geometry. So so there's a bijection, which is called this Van Quellen-Schaeffer's bijection. It's a bijection between, say, between quadrangulations and labeled trees. So basically, there is a process. I won't really tell you about the process, but there's a process by which, if you have a tree with labels on it, you do some specific process to it, and you get a quadrangulation, right? So, and this bijection has been exploited a lot to gain lots of information about how these uniform quadrangulation should look like. So the basic philosophy is that you have this bijection, and on one side you have trees with label process on it. So you try to take the scaling limit of both these objects, of these trees with the labels on them, right? And then that's how, once you take the scaling limit on this other side, on this tree with label process side, you sort of, and then you apply, in the limit, you apply your Schaeffer's or Van Quellen-Schaeffer's bijection to the limiting object. You might hope to understand what the limiting object should look like. Right, so this object, where you take this continuum random tree, which is the scaling limit of trees, a uniform measure on trees, say, and with the independent Brownian motion on it, which corresponds to the label process. When you apply Schaeffer's bijection, this Van Quellen-Schaeffer's bijection to that, the object that you get is called this Brownian sphere, right? And then there's this result by Legal and Manan, where they show that if you take these discrete quadrangulations, with n vertices with, I mean, so So this mu n is the measure, and this dn is the distance function on this quadrangulation. So you scale the measure properly, where the scaling is given by n inverse. So you had a quadrangulation with n vertices, you scale it by n inverse, and now you have a unit volume object, right? So that's why you get a unit volume Brownian sphere. And so you have to scale the metric properly also. So it can be shown that the diameter of this metric is like n to the 1/4. So that's why you have to scale the metric by n to the minus 1/4. But once you do that, you converge to this object called the Brownian sphere, and that's the continuous model of random geometry. Right, so you got this continuous model of random geometry by taking the scaling limit of the discrete, but you could also just consider this continuous model and try to study it itself, and it will have some properties which you can try to explore. So yeah, that was for Brownian geometry. Now I'll tell you some stuff about what kind of results people, just for, to familiarize people with this area, to what kind of results, some examples of results which people work on in this area. Okay, I would really like to get rid of this thing. Seems like it's not possible. Okay, maybe this is better. Yeah, so these are certain examples of results. So the first result, as I mentioned in the last slide, that you have to do n to the minus 1/4 scaling of the metric to get your limiting object. So it can be shown that if you take this Brownian sphere itself, then its Hausdorff dimension is actually equal to 4. So by Hausdorff dimension, I mean you take this Brownian sphere and you try to cover it by balls of radius epsilon, and you try to count, okay, how many such balls do I need? And the answer is that you need about epsilon to the minus 4 many balls. So this is not the formal definition of Hausdorff dimension, but intuitively that's it. And you also have this phenomenon known as coalescence of geodesics, or confluence of geodesics. So this geometry, this Brownian geometry, or this Brownian sphere, is actually quite different from your usual Euclidean geometry, in the sense that in a usual Euclidean case, you can have lots of lines which they pass through, infinitely many lines which pass through one point, right, and only meet once. But this cannot happen in this sort of geometry. The picture is that, so you should think that there is this random space where different parts of it are somehow are independent in some sense. So as a result of that, there is these regions which are quite attractive. So all geodesics somehow want to go through those regions, and because of this, there is this merging phenomenon of geodesics which arises. So that's why you see this tendency of geodesics to merge with each other. And as an example of a result in this direction, locally, most points locally, almost every point locally has only one geodesic coming out. This is this example of a typical point P, but you might have certain special points P where you have, even locally, you have multiple geodesics coming out, and we try to compute the Hausdorff dimensions of these points. And so there's a result saying that this set has dimension 5 minus k for k stars, and it's empty if k is bigger than 6, greater than or equal to 6. Right. So, and the final result, which I'll just mention as an example, is that in this continuum metric space called the Brownian sphere, its volume measure itself, the scaling limit of the counting measure on vertices, that is actually equal to that is determined by the metric structure, in the sense that you can do a Hausdorff measure construction to recover the metric structure. Okay, so that was about Brownian geometry, but so this talk is about Liouville quantum gravity. So Liouville quantum gravity is it's a more general model than Brownian geometry, and let's now discuss that. It seems like this is dead. Oh, no. Okay. Yeah. So, right. So Liouville quantum gravity. This is a one parameter family of random geometries. So it's indexed by a parameter gamma, which lies in the set 0, 2. So for each value of gamma, you get a model of random geometry, right? And this is also related to random planar maps. So earlier you were looking at random planar maps which were uniform, and you were trying to take their scaling limits in the Gromov-Hausdorff sense, the scaling limit of the metric measure structure, right? But now, instead of sampling uniform planar maps, you change the measure on these maps. So here what I write is that you take the discrete Laplacian on the planar map, you take its determinant, and you take the c minus c over 2th power of that determinant, right? Where c is given by this complicated, not so complicated, but this formula, right? So yeah, so this factor determinant of the Laplacian raised to the minus c over 2, it has some other interpretations also. So you can think of it as you take a planar map model and you do another statistical physics model on the planar map, and you bias the planar map by the partition function of that. So in the sense that you might take a planar map and you might do an instance of an Ising model on the planar map, and then you look at the partition function of that Ising model and you weigh your planar map measure by that, right? What is my delta? Is it? The delta is the Laplacian on the planar map. It's the discrete Laplacian. When you take its determinant. So yeah, one interpretation of this is by these statistical physics models, and another interpretation is that you take this planar map and the determinant of Laplacian is 2 minus c over 2. It's like intuitively it sort of measures the number of embeddings of your planar map into c many copies of the real numbers. So instead of taking uniform planar maps, now you're weighing it by the number of embeddings into RC. So this is all some physics intuition. But I want to mention that these objects have been studied in the physics literature since like the 1980s. So, and hence you can see the name is also Liouville quantum gravity. But right, so if you take c equal to 0, then you are not really weighing your planar map by any extra factor. So that's c equal to 0 corresponds to uniform planar maps, and if you solve for gamma, you get gamma equal to square root 8/3. So when gamma takes this special value, which is square root 8/3, you recover the case of Brownian geometry, which we saw earlier. Okay, so yeah, so this is the model that we'll be looking at. And how do we define this model? So to define this model, you have to use this object called the Gaussian free field. So yeah, so I'll now talk about that. You take an open set, say you take an open set U in the complex plane. So you want to define a random function on this open set. Right, and the Gaussian free field H, it's intuitively it's defined as follows: that you take a uniform function phi with 0 boundary conditions on this set, and you weigh this law on the space of all functions with the uniform measure on the space of all functions with 0 boundary conditions by this factor e to the minus integral of the gradient square. So you want to you can think of Gaussian free field as some sort of like you have pinned the boundary to have 0 values, and you want some fluctuating random thing. Right, so now this is not really a definition. I mean, there are many problems with it. First of all, the uniform measure on this on these functions doesn't make sense, and secondly, the object that you get even after making this formal is not really a function; it's a generalized function. But yeah, so intuitively, this is the object. And once you have this Gaussian free field H, the gamma LQG, your gamma LQG random geometry, it is the random geometry which intuitively has this Riemannian metric. So you take this dx square plus dy square, a usual Euclidean metric tensor, and then you multiply it by the exponential of the Gaussian free field, so e to the gamma times the Gaussian free field. So you get a random surface which is sort of which is conformally equivalent to your usual in the sense that there is this local conformal factor e to the gamma h which you put in, but yeah, that's a conformal change to the usual Euclidean. Okay, so yeah, now I give you a vague definition, right? So, but now I'll tell you about how do we actually define these objects. Yeah, so there are 3 important. Sorry?
There is a side control on the bar. If you click that, if you move.
Oh, so what do I click?
The side control. You see the left, to left.
This thing?
No. On the bar there is annotate on the right side.
Oh, annotate. Side
control. If you can move it. Maybe.
I have no idea.
Maybe
it's best to just, I don't know. I have to give some privileges to someone. Yeah. So, yeah, there are 3 main LQG observables, at least for this talk. Right? There's once you have the surface, you can. I mean, you would naturally want to have an area measure associated to it. You would want to have a metric associated to it, and so earlier we were looking at spheres, so random surfaces with the sphere topology. But you might also look at random surfaces with a topology of a disk. Then you would also have this boundary, and you might want to measure the boundary length, right? So okay, so suppose you take the upper half plane. So okay, all these theories are supposed to be conformally covariant. So here I just take the upper half plane because it's sort of it's a nice surface to work with. But you can do a conformal change of coordinates to work with other open sets in the plane also. But say you have this upper half plane and you take a free boundary GFF on it. So it's a variant of a GFF. Let's not worry about that. You have a GFF on the upper half plane and you want to define the volume measure, right? So the volume measure, this is actually given by this Gaussian multiplicative chaos measure. So this is a theory that was developed by Kahan in the 80s. And this measure intuitively corresponds to e to the gamma h times the Lebesgue measure. And again, you have to take the exponential of the Gaussian free field, which is not directly defined. So you have to do some renormalization procedure, some other way to define it. And the way it works here is that you take this Gaussian free field h. H itself is not a function, but if you modify it, then it becomes a nice function. So you take h and you replace it by the averages of h on circles of size epsilon, right? And now it becomes a nice object. And you can now define e to the gamma h epsilon times dx dy, and then you do some rescaling, which is this epsilon to the gamma square over 2 factor. You take the limit as epsilon goes to 0, and you get a measure. So this object e to the gamma h dx dy is the volume measure. And by doing a similar procedure, you can define a boundary length measure. And it turns out that the natural way to define it for gamma is this, again, by the Gaussian multiplicative chaos, e to the gamma h over 2 times the Lebesgue measure on the boundary, which is R. Okay, so these are two things associated. One is the bulk volume measure and then the boundary measure. And then, okay. Yeah. And this guy above now. Okay. So now finally regarding the metrics, so you also want to be able to measure distances between points, right? So, and with this construction was actually much more complicated, because the main reason being that the metric is a more non-local observable, right? To make the metric between 2 points, you somehow have to look at all paths, and that is different from the volume form. So how do you define the metric? So intuitively, you want to do again the same procedure. You want to first mollify the field, and these metrics are supposed to be limits of these planar map metrics, right? Which are just these graph, the graph distance on the planar map. So the metric between z and w, we first mollify your field to some h epsilon. So I write h epsilon star because the modification is a bit different. But you have this modified field. Now you want to measure the metric between point z and w. So you look at all paths from z to w. You sort of integrate your noise over this, integrate the exponential of the noise over these paths, and then you minimize it over all paths. And then there is this a epsilon gamma, some constant factor. Let's not worry about that. There is some rescaling factor which appears as you send epsilon goes to 0. I'll point out that here you have gamma over d gamma. So okay, reason for that is that when you define the volume form, you had e to the gamma h, right? And now you want to define the metric. So if your volume form scales by e to the gamma, then your metric should scale by e to the gamma divided by the dimension. So here you cannot just, if you stick in just gamma here, it won't be like the natural metric associated with that. So for that reason, there's this ad hoc way of defining it, that you first compute this, you first associate a number d gamma to gamma by looking at random planar maps and like looking at the distance exponent there, and then you stick in that factor here, and then you take the scaling limit. Right, so this is so the upshot is that this object, it converges in the locally uniform topology as epsilon goes to 0, and you have this nice notion of metric on the upper half plane. So okay, I'll just mention that in the original works, so in these works, they worked on the whole plane, so they did not really do the upper half plane. But once you have the metric on the whole plane, you can extend it to the boundary, and that was shown in this work by Hughes and Miller. Okay, so now you associate it to an instance of the Gaussian free field, you have a nice metric on the upper half plane. Okay, right. So this is a simulation. So this is a metric ball. So let's suppose we take gamma equal to square root 8/3, right? That means Brownian geometry. This is the value for c equal to 0, and you draw the set of all points which have distance at most 1 from the origin, right? So so this is some metric ball in this geometry, and you can see that it's quite weird in the sense that it has holes. This is not what you see in your usual Euclidean geometry, right? Your metric ball does not have holes, and also you can see that the geodesics, which are these red things drawn, right? This is, I have a tree-like structure. So this is like this geometry also displays coalescence or confluence. And yeah, so I'll mention. So these are some examples of results. just to give you a flavor of the kind of things people study. So just like in Brownian geometry, you also have confluence in these models. So heuristics have this tendency to merge together. So that's why in the previous slide you saw that there is this tree-like structure. And then there's another result which I like, which I write because I like it. So if you look at a metric ball centered at 0, say a metric ball grown till it hits a point Z, then you can try to ask what's the dimension of what's the dimension of the boundary of this ball. So this is this ball, right? You look at its boundary. So it will contain the outermost boundary and also these inner bubbles. And it was shown that this thing has Euclidean dimension given by this particular formula. And the final result, which I mentioned, is that the LQG area measure itself, you might ask whether it is determined by the metric itself. And it was shown in this work by Gwyn and Jinwoo Sung, who is here in the audience, that you can do a Minkowski content construction to recover the LQG area measure. Right. Okay. So now this is for the introduction. So now let's get to the result, main result of the talk. Okay, so I told you about Brownian geometry, right? So in Brownian geometry, you saw that there is this Corey, Van Kel, and Sheffer's bijection, which gives you a lot of integrability for the model. So the state is that in Brownian geometry, there are lots of things which are known, and in LQG also there's lots of stuff which is known, but understanding is better in the Brownian geometry side. So for instance, there is this particular thing which I write. So okay, we discussed the Brownian sphere, but you can define Brownian surfaces with different topologies. Suppose you have a Brownian disk. This is an object defined in this paper by Bettinelli and Miamon. So you have the Brownian disk, and it has this particular integrable property, that if you sample a point uniformly from inside the Brownian disk and you look at the distance profile. So the process of distances dp comma x, where x varies on the boundary, you parameterize the boundary by the boundary length. Then this distance profile, it is actually equal. It behaves up to a constant shift as a Brownian bridge, right? So you look at this process of distances. So, so as a result of that, since the Brownian bridge itself, it has this nice property called it has this nice feature of having a finite quadratic variation, in the sense that if you take a Brownian bridge and you Brownian bridge B and you make this sum, you take an interval a comma b and you cut it up into mesh size of size 2 to the minus n, and you make this sum, then as n goes to infinity, this converges in probability to the length of the interval. So because of that, given the Brownian bridge itself, you can recover the boundary length measure. This is one consequence of this property for a Brownian disk. Given the distance profile, you can do a quadratic variation construction to recover the boundary length. So the result is that even though you don't have this integrability in the case for gamma LQG, even though it's not a Brownian bridge, when you look at this distance profile, you do recover this particular way of taking a variation process to get your boundary length. So yeah, the result is as follows: that you consider free boundary GFF on the upper half plane and take the LQG associated to it, right? Take the gamma LQG associated to it. Then once you consider this this variation process, in the sense that you fix A less than B in your real line, and you fix a point Z somewhere, so just fix any point Z in the upper half plane, and you try to consider this sum, right? Then as n goes to infinity, this thing converges to a constant times the LQG, the natural gamma LQG boundary length of this interval.
Is the boundary length something we can get a picture of from like these objectives?
Yeah, so it should be the scaling limit of the boundary length of the quadrangulation. So suppose you take a quadrangulation. You mean why there should be? So if you take a quadrangulation of, right, so the scaling is as follows: that if you have a uniform quadrangulation of size n, then its diameter should be of order n to the 1/4. So the dimension of the space is 4, and the boundary length there, if you just do the counting measure, if you count the number of vertices on the boundary, that is by the level of square root n. So that's the Yeah, so that's where the half exponent comes in there. So this is for uniform, the uniform quadrangulation thing. But if you're doing LQD, then you're not taking the uniform measure. So now the scaling is different. Yeah, but here, so yeah, I said that I mentioned that the d gamma for the Brownian geometry case is d square root 8 third, that is 4. So when you stick in 4 there, you get 4 divided by 2 equal to 2, right? So you can recover the sort of quadratic variation result in the Brownian geometry. So here there is this mysterious constant k kappa, so sorry, k gamma, right? The kappa gamma. So yeah, so what is this constant? So now I'll okay. So yeah, I'll now tell you about that, this constant. So yeah, and this will be useful in the discussion of the proof that we'll also do in a bit. So yeah, so one aspect, sorry. Yeah, so one aspect here, which you can see, is that the left-hand side is dependent on z, right, on this fixed point z, but the right-hand side is not really dependent on z. So there's something going on here that as you send epsilon or n goes to infinity, the dependence on z is going away. So, and that's what you'll see here. So yeah, so this is a stronger form of this property known as confluence or coalescence of geodesics that I mentioned about earlier. So I realize that this is a bit dense, but this is one of the few places where it's so dense. So what's this event? So you look at, so this is your real line, and it's up above it is the upper half plane. And you look at the event that from the semicircle of radius S1 around the point X and the semicircle of radius S2 around the point X, right? You have two semicircles. And the event that all geodesics from this inside semicircle to the outside semicircle, they sort of meet at a common point. So it was shown in this work by Gwynn, Pfeffer, and Sheffield that so they worked in the complex plane. So they, instead of having these annuli, they had circles. But they showed that this event has positive probability, that all such geodesics meet at a common point, right? So this is a stronger form of this confluence of geodesics, that you sort of want all these geodesics to meet at a common point, right? And so once you have this event, you can start doing it at many scales. You say take an exponentially growing sequence of such annuli, and you can show that okay, it might not, this event has positive probability for one annulus, but as you take an exponentially growing sequence of annuli, it will almost surely happen for some annulus, right? And then you can get a sequence of coalescence point going off to infinity.
You require your M to be fixed and not random number?
You know, so here it says, sorry, so I should have said about M, but you can take a fix a large M. If there exists a M large enough such that it happens, and then
I think you cannot.
yeah, once you fix an M, and then you can take an exponential growing sequence. So yeah, once this happens, you can just you have this sequence of coalescence points, and this allows you to define infinite geodesics starting from any point in the upper half plane. So right, so the point is that if you were going from the point X to any point far away, you must go through the coalescence point. And there are these infinitely many coalescence points. So you can just string together geodesics to this coalescence point and get a infinite geodesic. So this sort of gives you a tree of geodesics in the upper half plane, right? And then and then you can define this object called a Boseman function, which is this notion taken from at least I'm familiar with in the case of first passage, last passage percolation. So you define it, the Boseman function, intuitively, it's like the distance from infinity. But the problem is, okay, you cannot define distances to infinity directly, but you can make sense of differences of them. In the sense that if you want to say define the distance of the difference of distances from infinity to -2 and -1, then you have these infinite geodesics, which you know that they meet. So they meet at a common point A, and you just take the difference from A to these 6 points, right? And this constant k gamma, which we saw in the last slide, that is given as a simple moment of this Boseman function. So you take this Boseman function between 0 and 1, you take this d gamma over 2th moment, which you can show is finite, and that's your constant k gamma. All right. So yeah, now we'll start discussing more about the proof. And one of the main tools used in the proof is this result by Sharmov. So, okay, so you want to show that there's some object, some variation object is equal to the Liouville quantum gravity boundary length, right? So there is this result by Sharmov which sort of gives an axiomatic characterization of the boundary length measure. So in the sense that suppose you have a measure, a random measure which is coupled to a Gaussian free field, right? A measure lambda h, which is actually measurable with respect to your GFF, and it agrees with your boundary length measure at the level of the mean. So that, as in, if you take your any measurable set, then it's on average its measure is equal to your the average of your boundary length measure. And also, if you satisfy this thing which I call gamma Weyl scaling, in the sense that if you add a function, if you add a nice enough function phi to your field, and then you compute your measure, the new measure that you get for the field h plus phi, then it is you just take the usual measure for h, and you do a simple Redon-Nikodym derivative of e to the gamma phi over 2 applied to it. Right? If you have a random measure which satisfies these three properties, then it is known that it must be equal to the LQG measure, LQG boundary length measure almost. So this is a h.
The small h. Lambda.
Oh, sorry, the small h, h, right?
Yeah, the lambda h, like your index h.
So h is say a Gaussian free field, a free boundary Gaussian free field on the upper half plane, and lambda h is a yeah, sorry, I shouldn't mention that, but lambda h is a measure which is coupled to that. So it's a measure which is a function of that.
So it's not like an actual random measure, but you're related.
It's a there should be a Gaussian free field, and this is some measure which is a function of that Gaussian free field. What function exactly, you don't know. But if it's some function of the Gaussian free field which satisfies these properties, then it must be constructed as the Gaussian multiplicative chaos construction.
So this proof should rely on the property of Gaussian free field.
So the proof of this thing? Yeah, so you're saying that you want to have a statement but there's no Gaussian free field, and there's a
because if that's not actually random measure, you are somehow defend related to GFF, then the proof might be only works for the GFF measures. Yeah,
so the statement is about the GFF, right? Statement is about the GFF. Okay. So I'll now mention some the broad overview of the proof. So you want to use Sharmov's theorem at the end, right? So the first step is to obtain subsequential limits. So you take these free-limiting measures, which I write as tilde nu and h, right? So you have this dependency on z also, so that's on the superscript. But you take this you want to work with the measure on the whole real line, but let's just fix the interval -1, 1. I think everything is once you do -1, 1, it's the working with the whole real line is fine. So you just want to show the variation process converges on the interval -1, 1, and you make these pre-limiting measures for this. So you basically just delta U denotes the Dirac mass, the unit Dirac mass at the point U. You take this pre-limiting measure, the sum over the Dirac masses, and you want to send n goes to infinity. So first you show tightness of these measures and obtain subsequential limits. Right? So you look at the law on pairs h comma nu and h, and you take n goes to infinity to obtain subsequential limits. So that's the first step. You get tightness, and once you have these subsequential limits at hand, you want to characterize them. So, and for that you want to use this result by Sharmov. So you want to get equality at the level of the mean. So, which is the second point. You want to show that up to this constant k gamma, which is this moment, you have equality with respect to the usual boundary length measure, and then you want to show this Weyl scaling. So in the sense that if you have a subsequential limit of both h and h plus phi, you have this nice Redon-Nikodym derivative relation, right? So once you have this, there is another step of showing that this measure is actually is actually measurable with respect to h in this coupling, and then you can apply Sharmov's theorem. So that's the broad overview, and right now I'll tell you more about the steps 2 and 3, because I think they are the most interesting steps. So the first part, actually, this tightness part, the arguments for that are somewhat similar to the arguments which are used in proving the Gaussian multiplicative chaos measures construction itself. Right? So when you take the GMC measures and you want to show that the pre-limiting things converge to a measure. There are some arguments there. So the first part is the tightness part is you compute certain moments. So it's similar to those, but I think the most interesting parts are the second and third parts. I'll focus on them right now. So okay. So suppose you already have a subsequential limit, right? You have the subsequential limit new edge, a new edge raised to z, right? And you want to show that its expectation agrees with the expectation for your usual GMC measure to a constant. So again, you see that the left-hand side has this dependency on z, and you want to get rid of the dependency, and you want to do it by using confluence. Okay, so what's the picture? So you look at all points on the interval -1, 1, right? And so you discretize it. You make this lattice of 2 to the minus nz, and you call the points, you call some of those points good. So the good points are those for which the coalescence event happens. Recall the coalescence event which I mentioned. The coalescence event was that if you look at all geodesics from the inside annulus to the outside annulus, then they all meet at a common point W, which is this confluence point. Right? That was the coalescence event. So you fix two constants alpha 1 and alpha 2, which are you fix them. So the 2 to the minus n times 1 minus alpha 1 is like much bigger than say 2 to the minus n. The picture is that since that coalescence event happens with positive probability for two semicircles which are say at constant distance away, you can iterate it to get that it happens with large probability. So then for most points on this lattice, on this mesh, this coalescence event is occurring. And not only that, you can do an argument to show that these good points, they actually carry most of the mass for your pre-limiting measures. Sorry, so yeah, recall these pre-limiting measures that we constructed, right? We summed up over these small distance increments raised to d gamma over 2 times the Dirac mass at u. Right, so your good points, you can show that they asymptotically have all the mass. So, right, you have most of these points are good and they asymptotically have all the mass. But once you have a point which is good, you can use it to get rid of this dependency on z. So, okay, so let's see why that is true. So you have a point u which is good, and you look at the variation, the mass that this pre-limiting measure gives to that point u, right? So that is just this difference. You look at the distance from z to u and the distance from z to u plus 2 to the minus n. You take the difference and raise to d gamma over 2. But since you have this confluence right around a good point, so all geodesics to points outside of this bigger annulus are also going through this point w. So in particular, the infinite geodesic, all infinite geodesics from points inside the smaller annulus are also passing through w. So you can just replace this sum, right? When you have this sum with z to u minus z to u plus 2 to the minus n, you can just replace z by w here because everything is going via w. So as a result of that, you can simply even replace w by infinity. I mean, the upshot is that it does not matter what point you take, as long as you have confluence. It does not matter what specific point you are really working with, because there is merging happening, right? So for good point, you can just get rid of the dependency on z, and once you have this infinity, this difference of distances to infinity is just the Bose-Mann function. So you can just replace z by infinity. And since all your mass was anyway, asymptotically all your mass was contained in the good points, you can just assume z equal to infinity from now on, right? But once you are in the case where you're working with z equal to infinity, it's very good, because see, the GFF itself has some scale invariance properties, right, which I did not discuss. But so you want to use the scale invariance properties of the GFF to get the get the first expression. So the problem with z being a finite point was that when you do a scaling of your space, the finite point z goes to another point, so you don't have any way to relate it. But now if you put z equal to infinity and you scale your upper half plane, then the infinity stays fixed. So as a result of that, there are certain nice symmetries which you have for Bose-Mann functions, which you don't have for distances from finite points. So for instance, if you want to compute the expectation of this moment of the Bose-Mann function, you can use your scale invariance properties of the GFF which I will not discuss in detail, to sort of write it in terms of the Boseman function from 0 to 1. Right, and so yeah, and you can use this in this property of the Boseman function, and then once you write it down, it's not very hard to show that this expectation of your LQG boundary length measure itself must be equal to the term there. Right, so the idea is to first use coalescence to pass to infinity, and then once you are working with z equal to infinity, you can exploit properties of Boseman function. Okay, so this was for like how do you show the mean, and it agrees at the level of the mean. Okay, and yeah, now I will tell you about the Weyl scaling. So that also heavily uses coalescence. So again, so you want to show this, that if you have a subsequential limit, d nu h plus phi and d nu h, both of them on the same space, right? And then you want to show that the measure for d nu h plus phi, that is equal to a Radon-Nikodym derivative applied to your measure for h, right? So again, you define good points. The good points are now the points which are good in the sense of the previous slide, but for both h and h plus phi together, right? So you want to have coalescence for both the fields h and the field h plus phi. And again, again, you can show that most of the measure for both h and h plus phi are sort of, supported on these good points, in the sense that if you look at the measure on outside the good points, then that goes to 0. So you can pretty much assume that all points are, that the points that you really care about are all good. Okay, so now we have a good point u, right? And so what you want to do is you want to show this above thing, right? So first you observe this fact that if you have a good point u, then this Boseman function, right, this bh u and u2 plus 2 to the minus n, you can just write it in terms of a completely local object. So the right hand side, in the right hand side, you are taking distances from the outside semicircle here, outside semicircle to the point u, and the outside semicircle to the point u plus 2 to the minus n. But once you do this, the point is that all your distances are completely local, in the sense that when you're taking distances to the semicircle to the point u, your geodesics are not really going to exit the semicircle, right? So you are basically going to all the action is happening in the region bounded by the outside semicircle. So now you want to sort of do a Taylor expansion for your function f, your function phi, that was assumed to be smooth enough, right? So okay, yeah, you want to what you basically want to show is that if you take this expression, this I'm sorry, yeah, here. So if you take this expression for h plus phi, right, and then what you get is the expression for h times this multiplicative factor of e to the gamma over 2 times phi of u. And to see this, as I mentioned, you do this Taylor expansion. So you have this function phi. So since you are everything is all the action is happening in this region around the point u, you can expand this function about u, in the sense that locally in this in this small circle around you, in the small semi-disk around you, phi is basically looks like phi of u plus some lower order term, right? So if you have any path which is lying completely inside this semi-disk, then its length in the h plus phi environment and the h environment, those lengths are just related by this by this factor. Since there are some lower order terms also, but the main contribution is e to the gamma over d gamma times phi.
You know how W changes when you have. It's going to be a different W.
The point W.
W depends on H.
Yeah, W should depend on H. Yeah, that's right. Yeah, W depends on H, but once you have some W, you can just write it as a distance from the semicircle, from the outside semicircle, right? Because once you have W, yeah, W will change. But you can even the distance from the semicircle, outside semicircle will you can just write it as differences from that, and those semicircles stay the same, right? So then it's okay. Yeah, thanks for the question. Right, so once you do that, you use this Taylor expansion property, and then you can write this the small, I mean, this pre-limiting nu n h plus phi, the amount of measure it gives to you, you can write it as e to the gamma over 2 times phi times the corresponding thing for the edge, field edge. So yeah, this is the sort of rough outline for how you show these two properties. So, and yeah, I think, okay, so I did not need any extra time. So I think that's it. Yeah, thanks for your attention.